Hello students, welcome to the physics class once again. Uh, in the last class we studied the potential concepts, capacitance concept and the derivations, those theoretical concepts we studied. Today let's study about the numericals. Okay, in this session you are learning about the electrostatic potential numericals. Okay, let's look at the first numerical here, the problem number 1. Calculate the electric potential at a point 0.3 meter from the center of the charged sphere of charge 15 microcoulomb when it is placed in air medium and in a medium of dielectric constant 5. Okay, now here in this case they given on charge that is 15 microcoulomb, and we have to find that electric potential at a point of distance 0.3 meter. Okay, once we have to find out this potential in air medium, and we have to check the potential in other medium. We don't know what that other medium is, but it is having a dielectric constant 5. Yeah, let's see the solution for them. They given the distance r is equal to 0.3 meter. We have to find the v air, and dielectric constant epsilon r is given 5, and v medium also we have to find, and that is a q value they given 15 into 10 power minus 6 cool. And we have this formula v is equal to 1 by 4 pi epsilon q by r. Use the same formula for the two different mediums. First find out for the air medium, substitute the values. 1 by 4 pi epsilon naught value is 9 into 10 power 9, and substitute the charge value as 15 into 10 power minus 6, and the distance r value is 0.3 meter, it's given. So you get the v air as a 450 into 10 power 3 volt. Next, to find out in the different medium. Okay, to find out in a different medium we have this formula with respect to the air medium. V medium is equal to V air by epsilon r. Okay, so for the above formula V epsilon naught, if we divide the epsilon r there, or if we multiply at the denominator epsilon naught into epsilon r, so that defines the potential at any medium, right? So here we can directly use this formula. V medium is equal to V air divided by epsilon r. V air we already calculated here. Substitute the epsilon r value, then you will get the V medium as a 90 into 10 power 3 volt. The next one, problem 2. A point charge of 10 into 10 power minus 8 coulomb is at a distance of 1 meter from another point charge of 20 into 10 power minus 8 coulomb in air. Okay, so these are the 2 point charges. One is a 10 into 10 power minus 8 and another is a 20 into 10 power minus 8 coulomb. These two are kept in a air medium and they are separated with a distance of 1 meter. We have to find the electric potential at a distance 0.2 meter from the weaker charge. Which one is a weaker here? 10 into 10 power minus 8 compared to 20, 10 is the weakest. Okay, we have to find out at a 0.2 meter distance from the 10 into 10 power minus 8 coulomb what is the potential. Yeah, look at the solution. Here q1 and q2 are separated with a distance of 1 meter. Okay, we have to find out the resultant potential at the point P, and the point P is located at a distance of 0.2 meter, okay, from the Q1. Then the remaining distance will be 1 minus 0.2, right? So we have a formula that V is equal to 1 by 4 pi epsilon naught Q by R. First let's check the resultant potential here. Okay, the resultant potential at that point P is the sum of the two potentials. One is the potential from the charge 1 and another is the potential from charge 2. Therefore the resultant potential will become V1 plus V2. So substitute the formula 1 by 4 pi epsilon naught Q1 by AP. So it's relevant to the first charge. So till the point P the distance is AP. Related to the second charge the distance is PB. Therefore the resultant potential Q1 by AP plus Q2 by PB. 1 by 4 pi epsilon naught is 9 into 10 power 9. Substitute the Q1 value and Q2 value, AP and PB value. Okay, and then simplify it. So you will get the 6750 volt. So this is the resultant potential at the point P. Next one, problem 3. The third problem, a charge of 20 microcoulomb produces an electric field. 2 points are 5 centimeter and 10 centimeter away from this charge along a straight line on the same side. Find the potential at these points. Also find the amount of work done to move an electron between these 2 points. Here they given only one charge, single charge, that is 20 microcoulomb. But they given 2 points. Okay, one point is at the 5 centimeter distance, another point is at the 10 centimeter distance. Okay, so 5 centimeter distance is the closest one to the point charge, and the 10 centimeter is little far away than the compared to the previous point. Okay, we have to find out the two potential here. One is at the 5 centimeter, one is at the 10 centimeter. Okay, and we have to find the amount of work done to move an electron. Okay, suppose we are moving an electron from one point to another point. Of course we need a work done to move, okay, against the electric field. So we have to move an electron here. How much the work done is required, that we have to find. Yeah, look at the picture. There is a charge 20 microcoulomb. V1 is the first point, it is located at the 5 centimeter, and V2, the second potential, we have to find there at the 10 centimeter distance. Okay, so now use the formula 1 by 4 pi epsilon naught q by r1 to find out the v1. Substitute the values. 1 by 4 pi epsilon naught value is 9 into 10 power 9, q value is 20 into 10 power minus 6, and the r1 is the distance 5 centimeter, so we can write it as a 5 into 10 power minus 2. So you will get the v1 value as a 36 into 10 power 5. Next, similarly find out the v2. So the small changes, we have to change the distance as a r2. Okay, for the distance till the point that v2 is from the charge q is 10 centimeter. So r2 will become 10 into 10 power minus 2. So after finding v1 and v2, we have to find the work done. So look at the formula work done, v1 minus v2 into charge to be moved. How we got this formula? This formula we got from the v is equal to w by q, from the potential definition. Okay, potential is equal to work done by the charge, right? So there we can write it as a w is equal to v into q. So instead of v, we can write it as a potential difference. So it is v1 minus v2 into charge to be moved. So we got the v1 value and here v2 value, substitute that, and charge to be moved is an electron. The electronic charge value is 1.6 into 10 power minus 19. So the value of work done is 28.8 into 10 power minus 14 you will get actually here. Okay. Next one is the problem 4. Two charges plus 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb are located 15 centimeter apart. At what points on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. There are two charges now located 15 centimeter apart. Okay, the distance between them is 15 centimeter. We have to find now at what point, at what distance the potential becomes 0. We can solve this problem in two cases. Yeah, observe, we can solve this problem in two cases here. The case 1, observe the two charges q1 and q2 kept at a distance r, that is the r, the distance 15 centimeter they given, and q1 is a positive charge, that is plus 3 into 10 power minus 8, and q2 is the negative charge, minus 2 into 10 power minus 8 coulomb. Okay, yeah, now first in the case 1, we are taken the point p in between the two charges. This is what the case 1. Okay, and at what distance the potential becomes 0? We doesn't know that distance. Let that distance be x. Okay, between that a and p, the distance I take it as a x, and the remaining distance will be the r minus x. According to the concept of resultant potential, it is v1 plus v2. Okay, and according to the question, resultant should be 0. Take it as a 0 and substitute the v1 value here, 1 by 4 pi epsilon naught q1 by x here. Okay, x means is relevant to the charge q1 till the point p. And similarly for the v2 is a, we have to use negative charge, minus q2, because you can see in the data the value is negative, right? So minus q2 divided by r minus x. R minus x is the distance between p and b. The second distance you have to use, then shift it to LHS, then you can cancel 1 by 4 pi epsilon naught, then you will get the values like this, q1 by x is equal to q2 by 15 minus x, because r value is 15. Now substitute the q1 and q2 values there. 10 power minus 8 will get cancels, then cross multiply it. Okay, then after solving we get x is equal to 9 centimeter. So the meaning is from the charge q1, from the charge q1 at the distance of 9 centimeter, the point p should be there. So at that point the resultant potential will become 0. So this is the case 1, we taken this point P in between the two charges. Now in the next case, we have taken this point P next to the lower magnitude charge. Which is the lower magnitude in this two? The minus 2 into 10 power minus 8 coulomb. Okay, the plus 3 is the greater one, and minus 2 into 10 power minus 8 coulomb becomes the lowest magnitude. So we are taking in the next case the point P next to the Q2. Observe the case 2. The point P is taken here, 3 into 10 power minus 8 coulomb, minus 2 into 10 power minus 8 coulomb, and the distance between the Q1 and Q2 is R. Now the point P is imagined to be somewhere near to the Q2, so we doesn't know that distance. Let it be x. Then the total distance become R plus x. Okay. Yeah, use the same concept. V resultant. Resultant potential is equal to V1 plus V2. The V1 from the charge 1. Okay, yeah, so v1 is 1 by 4 pi epsilon naught q1 divided by r plus x, the distance between the a and p, the total distance between a and p is r plus x, plus v2, for the v2 1 by 4 pi epsilon naught minus q2 by x, right, because the charge 2 is a negative, use minus q2, that divided by x. From q2 to the point p, the distance is x. Now shift it to LHS side, one term to the LHS, okay, and then negative will become positive. Then cancel the 1 by 4 pi epsilon naught, then substitute the value, then 10 power a minus 8 get cancelled. Then after simplification by taking the cross multiplication, you will get x value as a 30 centimeter. Okay, so at the lower magnitude charges side, at the distance of 30 centimeter, the resultant potential will become 0. So this problem we can solve in two cases. Yeah, similarly, here is the next problem, the problem 5. Two charges plus 1 nanocoulomb and minus 4 nanocoulomb are 1 meter apart in air. Find the position along the line joining the two charges at which resultant potential is 0. Okay, so take this as a homework, do it as a homework, try it by your own. Okay, by looking at the problem 4, you can solve it very easily, only the datas are a little changed, and you have to solve it in a two cases. Take it as a homework. Next, problem 6. Two tiny spheres carrying charges 1.5 microcoulomb and 2.5 microcoulomb are located 30 centimeter apart. Find the potential at a point 10 centimeter from the midpoint D of the line joining the two charges. Two tiny spheres are there. Okay, tiny spheres are charged here. One is of the charge 1.5 microcoulomb and second one is with the 2.5 microcoulomb. The distance between the two spheres are 30 centimeter. Now we have to find the potential. Okay, and at a point, this point located at 10 centimeter from the midpoint of the line joining the two charges. Okay, yeah, I'll show the picture, you'll come to know how to solve it. See, this is the picture. Now A and B, okay, we have to place the two charges there with the 30 centimeter distance. Observe the midpoint, the D is the midpoint. Since it is a midpoint, the distance get equally out, that is 15 and 15 centimeter. We have to find the resultant potential at the point C. Okay, at the point C, observe the point C is located at 10 centimeter from the midpoint, right? Now by using the right angle triangle concept and by using the Pythagoras theorem, we can find out the AC and BC here, right? Because here if you select the triangle ADC and the BDC, 15 centimeter and 10 centimeter, you get the two sides, and hypotenuse you can find out very easily by using this method, right? So AC or BC root 325, you will get 18 centimeter or 0.18 meter. Now we have to find the resultant potential at the point C. Okay, resultant means the potential due to the two charges placed at A and B. So the two charges We know that value, it is mentioned in a question. So take it as a resultant potential at C, BC, 1 by 4 pi epsilon naught, Q1 by AC plus Q2 by BC. Substitute all the values. The AC and BC will take the same values at the denominator, 0.18, it's converted into meter. And take it as a common denominator by taking an LCM method. 0.18, 1.5 plus 2.5 becomes 4, and 10 power minus 6 is a common. After solving, we get the resultant potential as a 1.999 into 10 power 5 volt. Here the next problem 7. ABC is a right angle triangle with AB 0.2 meter and BC 0.6 meter and ABC 90 degree. So it is right angled at the B point. AB is 0.2 meter, BC is 0.6 meter. A charge of 12 nanocoulomb is placed at the corner B. Find the amount of work done in transferring a charge of 6 picocoulomb. PC means pico. From C to A. This is the question. So it gives a picture of right angle triangle. Let's draw the right angle triangle now. Yeah. Observe the picture. This is the right angle triangle ABC. At the B there is a 12 nanocoulomb. The side AB is given 0.2 meter. The side BC is 0.6 meter. Okay, now we have to find the work done required to move a charge from C to A. The point from C to A. That we have to find how much work is required. Right. Charge to be transferred is 6 picocoulomb. Pico means 10 power minus 12. So it is written as a 6 into 10 power minus 12. First find out what is the potential at this point A due to the charge 12 nanocoulomb at B. Okay, here you observe only there is a one charge, that is 12 nanocoulomb. It is placed at the B. Okay, from that charge there is a potential at A point also, there is a potential at C point also, right? At a distance of 0.2 meter there is a one potential, that is VA. At a distance of 0.6 meter there is a potential at point C, that is VC. Okay, or VB you can take. First find out the two potentials here. Understand? First find out the two potential VA 1 by 4 pi epsilon naught Q by AB. Understand? That is a VA value you will get. Next find out the VB. For to find out the VB potential, you can take it as a VC also. Okay, 1 by 4 pi epsilon naught Q by BC. BC means 0.6 meter we have to use here. Then you will get the VB. After finding the VA and VB, then find out the potential difference, that is VA minus VB. Okay, by using the same formula to find out the work done. We know that work done formula, VA minus VB into charge to be moved. 540 minus 180. Charge to be moved is 6 picocoulomb. Pico means 10 power minus 12. So you will get this value in terms of joules. You look at the problem 8. Next one, little important, and we studied the similar problems in the first chapter too. Charge is 2 microcoulomb, 4 microcoulomb, 6 microcoulomb placed at the corners ABC respectively of a square ABCD of side x meter. So it is a square, side is x meter they given. At the three corners there are three charges. Find what charge must be placed at the fourth corner. We doesn't know what is the fourth charge should be. Okay, so that the potential at the center of the square is 0. To maintain the potential at the center of the square, okay, that means the diagonals intersection point. Okay, at that point we have to take the potential as a 0. To maintain that potential as 0, what charge must be kept at the fourth corner? So you have to find the charge value. Yeah, observe the square here. Again, there are a square A, B, C, D. Okay, Q1, Q2, Q3, Q4. Q1 is having the charge plus 2 microcoulomb, Q2 plus 4 and Q3 plus 6 microcoulomb. all are placed at the corners, right? If Q4 we don't know, we have to find out that Q4. So let's find out the length of the diagonal first. Length of the diagonal we can find out BD is equal to AC. Since both the diagonals are of equal length, root 2 into side. Side is a x root 2. Then find out the AO, BO, CO, DO. Those are the distance at the center from each corners. Okay, just dividing the length of the diagonal divided by 2, x root 2 by 2. Okay, you will get x by root 2. Now find out the resultant potential at O. The resultant potential at O is the sum of all the individual potential from each corners, right? So 1 by 4 pi epsilon Q1 by AO. Q1 divided by AO. AO is the distance till the point with respect to charge 1, right? And Q2 by BO. BO is the distance till the center from the Q2, right? And similarly Q3 by CO plus Q4 by DO. Substitute all the values AO, BO, CO, DO values all are equal here as we observed. X by root 2 it is, okay. X by root 2, x by root 2, x by root 2. Take the x by root 2 common out. Then we left with inside the bracket Q1 plus Q2 plus Q3 plus Q4. Send this denominator part to the left hand side. Multiply with the 0. Okay, 4 pi epsilon x by root 2. When you send to left hand side, it multiplied to 0. Then entire term will become 0. And now we will substitute the value for Q1, Q2, Q3. But we don't know Q4. Keep it as it is. So we got 2 plus 4 plus 6. So that is 12. And send that 12 to the left hand side. We got Q4 as a minus 12 microcoulomb. The meaning is if we place the minus 12 microcoulomb at the point D, then the resultant potential at the center of the square, that means at the point O, that will become 0. Thank you. Thanks for watching. These are the some bit of problems I discussed based on a potential. So in the next class we discuss the more numericals based on potential as well as on the capacitance concept. Okay. Yeah. Thank you.